All right, let's get started here. So there's two things you're thinking about or should be thinking about. One is the exam on Wednesday, 2 days from today. And the other thing is keeping up with the assignments and working on those. So you let me know. I think it's good to go forward and look at arrays because this is important. The rest of the course will be based on using arrays, and you'll have a lot of work to do with arrays. But some of you may want to focus today more on reviewing material that will appear on the exam on Wednesday. 50-50. All right, let's do it that way. Does anybody have specific questions or suggestions on what we want to look at for the review? There is some example problems here. I think it's pretty straightforward. The solutions are given here, for instance, for this one. Is there something that's confusing that I could go over, maybe some concept or one of the problems that you may be struggling with trying to understand in the example for exam 2?
I don't necessarily know if it's the example, but it was a problem that I came across when I was doing the lab. And when we had our variables and like brown egg is equal to brown egg for the egg carton, for example.
Yeah.
When I was doing that, I was experimenting doing it different ways, and you said that you don't always have to use this with the dash and the arrow thing.
Yeah.
And mine would not work unless I used this and the arrow. This brown egg is equal to brown egg.
Yeah.
And I was just wondering.
That's because the argument name here, see brown eggs?
Mm-hmm.
So this is the name that you gave the variable in the argument list to the function. Mm-hmm. So the argument that's passed into the function is equivalent to some storage location in RAM. Mm-hmm. And then there's this member variable with the same name, brown eggs. But that's a different storage location in RAM. So there's two different storage locations, but they happen to have the same name. So when the compiler is faced with that situation, it has to decide which name is the one you mean. And it takes a name that has more narrow scope, more narrow visibility, which is the name of that variable that's in the argument list to the function. So when you use brown eggs without this, it refers to that brown eggs variable that's declared as an argument to the function, not the brown eggs variable that's declared as a member of the class.
Okay.
It's like having two people in the room here with the same name. And, I could say Jill, and there's two Jills. Well, maybe it's you, and you're not Jill, but suppose you were Jill. I'm looking at you and I'm saying Jill. So then we say, given the context that the speaker is looking at that Jill, that speaker's talking to that Jill and not the other Jill. So the compiler has to sort of understand what name you mean and the context in which it's used. Now, and I'm talking to you now about the other Jill. I said the other Jill. Oh, now we know it's the other Jill, see? So you put this arrow brown eggs to mean the other brown eggs.
Oh, okay.
Anything else for the review? Maybe what you should do is work out the exam problems and try to get it on your own, the example exam, and try to come up with these solutions on your own. You should practice these as if you were taking the exam on Wednesday, and make sure that you get these right. See here, once again, here's the locally scoped seats. I say locally scoped. That means the name is visible for the code that's in the function. It's visible to the code that's in the function. This variable seats here that I've highlighted is not visible to code that appears outside of the function. So I use the word locally scoped, local to the function. But this arrow seats refers to the member variable seats. See, the seats in the function, when this function executes, there's something called a stack. And the stack is something, that grows. It's like a stack of plates, and you put plates on the top, you take plates off the top. That's called a stack. It's a data structure in computer science. And when a function is invoked, you have the arguments that are passed into the function are placed on this stack. Their memory is allocated on this stack. And then the function executes, and it can access that memory. And when you return from the function, the stack is popped. These temporary variables that are allocated on this stack are then deallocated. So they have a short life expectancy. They only live for as long as the function executes. And next, you can call the function repeatedly. Each time you call it, those variables are allocated in RAM, again, in this thing called a stack, used, and then discarded. But now what we want to do is preserve the state, preserve the values that are passed in. So we have these objects that we have these instances of the school bus class in this case, or instances of the egg carton class. These instances have their own scope, and the functions that run against them have a more restricted scope. So you have to think about that. The school bus instances that are created in the main function, let's see if it's in here, provide test code. Here, this code here would be inside the main function. So actually, this bus instance is also created on the stack, but we don't return from the main function right away. What we do is we invoke these functions on the, I'll call that one there. This is a function that takes an argument. That 4 is being passed in to a variable, an argument, a variable name that appears in the function's argument list. Now this variable, this named variable, takes on the value 4, and see, when main is called, we've got memory allocated in RAM to store this bus object, and then when this function is called, that additional memory is putting more plates on the stack before we return from main. So we didn't deallocate the bus object yet. It's still sitting there, in controlled memory, and it's considered allocated and addressable. And then when we invoke this add students function, additional memory is created in this stack structure to store that value 4. And that's used during the execution of the function. What happens is, when this add students function runs, it takes the value that's stored in memory and copies it into the students variable that's in the bus instance. And then we return from this add students function, and that 4 that got passed in is then discarded. But we copied the 4 into the bus instance, so that it's preserved in that object. Of course, when we get to the very end of the main function, return from main, then the bus object is deallocated. So You get a better grasp of this when you study some other courses. There's a course called 313, CSE 313, on computer organization, and it goes into how this program would execute in the hardware. You know, what happens in the CPU, what happens with RAM, what happens with the register memory in the CPU. So when you start looking at those details, then you get more confidence and a deeper understanding of how these programs written in higher level languages execute. So for now, you know, you're stuck with the task of developing some kind of mental models that you can use to solve problems with. You know, you're writing code, you're tasked with writing code in this language, C++, to solve certain problems, and you need to somehow develop the right notions and concepts that you can apply to creatively apply in the solution of these problems. So I'm trying to convey those ideas to you that I believe are useful to you in solving these problems. But for a deeper understanding, you need to look at other concepts. You need to acquire other knowledge. You need to understand more about what's going on at the hardware level, and maybe at the operating system level, in the CPU, what's happening there. Once again, it's not a topic that we're covering in this class. So, you know, you're just stuck with the problem that you can only have a limited understanding of what you're doing. And that's, if you keep working at this and chiseling away and go through additional courses and pursue your own personal sort of research agenda related to this, and you'll get better and better knowledge and mastery of this subject material. All right. I think that's enough there. Here, seated students is a member variable, but we don't have to put this in front of it because there's no variable in the function that overshadows it. Doesn't appear in the argument list of the function, and it's not declared. It could also be overshadowed by a local declaration inside the function as well, but that doesn't exist either. So this name, seated students, the compiler says, oh, that's the member variable, seated students. And so that's what I'm going to use. So we don't need to, but we could put this arrow seated students in front of it if we wanted to. And some languages actually require you to do that. But in C++, Java, and C#, they do not require. Those three languages, big languages in particular, don't require that. But I think Python requires you to annotate all of the member variables with, I think it's self dot seated students. I mean, you're forced to use that extra annotation to indicate that the variable is a member variable. All right, I think that's enough on that. It's hard to really grasp this unless you work the problems out on your own and you read and think about it. Yeah?
Will the exam be similar to the practice to where we're...
Yeah, this practice exam was a copy of an earlier exam I gave in this class. This is exactly the exam. So you can see something like that. Here in this exam, I could ask it in different ways. So it may not be exactly like this. Oh, here, draw the UML class diagram. So I may ask you to draw the UML class diagram, or I may give it to you. And I might say, here's the UML class diagram. Define or declare the class. Give me the code that declares the class, and you would produce that. So you can go from this code to the UML class diagram, or I could give you the UML class diagram, and then you could produce this code. So there's a mapping between those two representations. You can go from one to the other. And then I'll certainly be asking questions like this. Provide an implementation of a constructor. For sure, I'm going to ask you to do that. And yeah, the exam will look a lot like this, just like that. 9 problems, maybe there'll be 8 problems, something like that. All right. Let's look at Lab 6 on arrays. An array is a sequence of data items. So what we've been working with so far in the course are single instances of data, like an integer called x, another integer called y. Now we're going to work on a collection or a sequence of integers, like 100 integers, one next to another in a sequence. And there's 2 ways of representing these sequences. Well, maybe more than 2 ways, but we're going to look at 2 different ways of representing sequences of data. And one way is called an array, and that's the syntax. This is a declaration of an array named A, which is a sequence of integers, or int. And this is an argument to the function myMaximum. And here's the other type of sequence that we're going to look at, and it's called a vector. Here we're declaring a variable v, which is of type vector. Well, it's a reference to a vector. That's what the ampersand is. I'll talk about that a little more later. And the data type is given here. See, so it's a sequence of int, but we could have a vector of string. We could have a vector of school bus. We could have a vector of double. So you can have a vector of any data type, primitive data type, or user-defined or complex data type. So we'll start by maybe solving this exercise 1, and then I'll talk more about the syntax and the idea of a sequence of data. There we go. There's our hello program. That works. Okay, so now we have a container for the code we're going to write. So exercise 1, finding the maximum value. So what this exercise is about is to define a function called myMaximum and pass in an array of integer and the number of elements in the array, and then return the maximum value.
Sorry, Professor.
Not a problem.
It's the Daniel's fault here.
All right. So here's the function, myMaximum. I didn't call it maximum because in some of the header files they refer to a function named maximum, I think. So I wanted to avoid that possibility anyway. So myMaximum takes an array of integers, a sequence of integers. The thing about arrays, which are different than vectors, is that when you're given an array variable, you don't know how many items are in the array. You don't know how long the sequence is. So that's a piece of information that you have to store separately from the array itself. So that's the second argument to the function, number of elements. But that's not necessary for vectors. Here, that n is not the number of elements in the vector, because the vector is a complex data type. It has functions in it that you can call. One of them is the size function. It gives you how many elements are in the vector sequence. But arrays are a more primitive data structure. Actually, the C++ language evolved out of the C language. The C language is a subset of the C++ language, and the arrays exist in the C language. So this syntax is good for the C language, but vectors do not. The vectors were added to the language as it evolved into C++. All right, so maybe I should read the instructions here. Provide an implementation of the myMaximum function, whose declaration is shown above. The first argument of the function is an array of int, and the second argument is the number of ints that are in the array. The function returns the largest int that is in the array. Write test code that thoroughly tests the function. The test code should use assertions. So we're going to be writing test code. And we'll have assertions.
We need to include the C assert, right?
Thank you. Yeah, that's right. We need to include CSUSB. Very good. Thank you for that. So let's see what the code looks like when an assertion fails. I'll just pass in false directly, just to see if I got everything working right. Control reaches end of non-void function. Oh, here. See, I'm trying to compile this as a stub, but here the function is declared as returning an int, and the compiler is telling me that that we need to return something. Actually, I think that was just a warning, wasn't it? Let's just return a 0. So I'll eliminate the warning by returning a value. So we'll eliminate that warning message. So it's a warning actually that compiled. So it actually compiled. It was just a warning. But if we compile again, then we don't get the warning. Well, we get the same behavior. All right, so what we need to do is call this thing. Oops, that's not it. So we're going to call this function myMaximum. We're going to pass in an array, say A1, and I'll call it A. And let's put 4 elements in it and get the return value. Suppose the maximum value is 8. So I'll call it max equals myMaximum. And then we'll assert that, that max equals 8. Of course, if I just do this, it'll pass. But we want it to search through an array A with 8 values in it. I'm sorry, 4 values in it. We need to declare the array. Here's one way to do it. And I got to do this, I have to remember, I think this is how to do it. This is a convenient way to do it. Here I'm declaring an array A that has 4 values in it. The first value is a 6. Second value is -3. Let me just check to
And it
make
can be just any 4 values.
any 4 values. Yeah. Let me just check to make sure I got the syntax right. I did. Okay. This syntax is not supported in earlier versions of the language, I believe, but I think it's widely supported now. And you see this in other languages as well. There's another way to allocate arrays. I'll show you an alternative. We can create an array, say B. Actually, I'll put it underneath this stuff here. I'll use a different syntax. And I got to do it from memory here. So I create an array B with 3 items in it. Let's see if that compiles. It does. And then I'll assign the first value. Actually, I'll make this equivalent. So this will be B will be equivalent to A. So B has 4 values. And we use this syntax here, these square brackets, with a value in between them, to identify a position in the sequence. So the position 0, that's the first position. Remember, in computing, normally counting starts at 0. So we label the first. It's like if you had seat numbers. We would, as humans, we would say seat 1, seat 2, seat 3. But the computer likes to start at 0, so that the computer likes to label seat 0, seat 1, seat 2, like that. So the first item in the array is item 0. Oops. And the second item is -3. The third item, which is item in position 2, is 8. And the fourth item is 1. So these are equivalent. A and B are equivalent. So we should get the same result here.
You went 0, 1, 2, 4. What about B3?
Oh, I'm sorry. Thank you.
It's supposed
Very
to be
good.
B3, right?
Yeah.
You started 0. So.
Thank you.
If we use B though, wouldn't we have to do at the very top under using namespace standard, wouldn't we have to say B instead of A brackets?
No. This is just that's a separate name. They just happen to have the same name. It's just a coincidence. Like there's 2 Jills in this class. I mean,
Oh.
yeah. Just the same name, but the 2 different things. This A is different than this A.
Oh, okay.
I called it A because it's going to be copied. This A is going to be essentially copied into this other A.
Okay.
Actually, the vector is not copied. A is called a pointer to the vector, to the array. And we copy the array pointer when we call the function myMaximum.
I have a question.
Yeah.
Okay, for A, there A up there, why do the brackets leave it empty for B leave it 4?
Because here the compiler can understand how many items are in the array. The compiler can deduce because I'm providing the list. I'm providing the initialization data. So the compiler can count and says, oh, you have 4 items, I'm going to allocate 4 slots. Here, we're just saying, hey, I'm on an array. Okay, I'm not going to tell you what goes in it yet. When the compiler says, well, how big is it? So it needs to know the size in advance. Array sizes are fixed. Once they're set, they cannot be changed. Vectors are different. The size of a vector can be changed. Yeah. That's so here we need to specify the array size 4. And then we go through and do the initialization like this. So this A and B produce the same array, and we hopefully get the same result when we test it. Well, we set this up so that we're going to get you know, the correct result. So we have our stub returning 8, which is the correct number. So that should print all tests passed.
So you said it doesn't matter whether we use the int a equals that set, or if we use the int b and then claim everything individually?
Exactly. You can use either approach. But actually, returning 8, this is not quite right. We need to do this implementation. So let's figure out, how do we determine the largest number in an array? By the way, this is these problems on this this assignment. All of these problems are potential exam questions, exactly as they're stated here. So these are small, relatively easy to code problems. I think that's why I have a lot of them there. And this could be an exam right there, these 10 problems. But actually, in the exam, I would probably ask here, I would ask for the implementation of my maximum without the test code. And maybe in the second problem, I would ask for some sample test code that tests your implementation. So what we need to do is we need to scan across the elements in this array, in this sequence of integers. We need to scan across the elements and keep a record. Each time we see a larger element, we're going to increase our record of the biggest thing that we've seen. So let's create a variable that's going to store the number. We're going to create a variable. Let's call it m, which stores the largest value that we've seen. We're going to look at the first element, second element, third element. Each time we see a larger value, we're going to change the value of m to represent the largest thing we've seen. Now, if we look at every element, then what m ends up being is the largest value we've seen, looking at everything. So it's the largest value in the array. And the question is, what's a good starting point for n?
The first number?
Yes, that's very, very good. The good starting point for m is the first value in the array. We can't start at 0 because there's a -3 in there. What if the array had all negative values? If we started at 0, we wouldn't get a right result. And so let's range for all the valid indices for the array A. So we'll start at 0. That's the first location in the array, location 0, position 0. And let's continue, but exit the scan as soon as I hits the number of elements. Elements. So if the value that we're currently looking at, which is A of I, if it's bigger than our record of the biggest that we've seen so far, then let's set our record of the biggest to A of I. So A starts at 0. Look at this code here. What values does I take on? For what values of I
It's gonna first
does
start off
this
with-
code run? So, well, this code here that I'm highlighting right here, this will run when the loop condition is true. So for all values of I that are strictly less than number of elements, for all those values, this condition will run. In our case, I will be 0, 1, 2, and 3. As soon as I hits 4, actually I does hit 4. I does hit 4. When we increment, when I is 3, the loop condition is true because number of elements is 4. When I is 3, the loop condition is true and we execute this line. So we execute this line when I is 3. And then at the end of the loop, we increment I, so I becomes 4. Now when I is 4, the loop condition is false because 4 is not strictly less than 4. So we do not run this part, the body of the loop when I is 4. When I becomes 4, we exit the loop and we go to the next line. So that's what we want. We want this line to run for I equals 0, 1, 2, and 3. What do we return here?
M.
Well, it's either I or M.
You can also return 8.
Yeah, we could return 8. We could return 9. Huh?
It's I.
No. Oh, it could be I and it could be M. It depends on how the problem is stated. Do we want to know the position of the maximum element, or do we want to know the value of the maximum element? The problem asks for the value of the maximum element. It does not ask for the position. But I could, on a test, ask you, write a function that returns the position of the maximum element and provide test code for that. And in practical situations, that's what you want. You want to know the position of something. You don't want to know the value. You already know the value. You already know. You want to know the position of something. So, but what we need is the value of the maximum in this problem, not its position. That's actually one of the things that that students are confused about from the beginning when talking about arrays and vectors. And that is the distinction between positions and values. So you've got the array is a sequence of values, and each value is at some position. The first position is position 0. The second position is position 1. Well, what's stored in position 0 could be anything. Could be a -10. So you need to, when you're looking at variables and you're thinking about the problem, you need to be careful to distinguish clearly between a position and a value. I mean, a position is a value. It's between a position and the value at that position. I should say it like that. A position is also a value. The 0, the first position, is a value. I represents a value. It's the position value. So you need to distinguish between the position and the value at that position. So I think this should work. I'm going to get rid of this. All tests passed. Let's have another example. There's an array that's all negative values. let's see that, because we've talked about the problem of initializing this search. And then if we made the mistake of initializing to 0 rather than to value at 0, if we make this mistake, then this is test code here that will reveal that bug, reveal that mistake. Because this is an array that has all negative numbers, and the largest number is -10, but that's less than 0. So let's watch this code fail. So it's a better idea, or it's a better idea. There's other ways of doing it. So it fails to initialize m to 0. We don't know. Maximum value could be a negative number, so we start with the first value in the sequence. There's a small adjustment that we can make to make the program run a little bit faster, an unimportant amount. Anyone tell me what that is? We're doing something we don't need to do. Anybody know? See, we already set m to the first values. We don't have to check that.
So then I equal m.
Just start at 1.
Oh, okay. You've already set it up as the first number, so you
Yeah.
set it as the second position.
Exactly.
The first one.
And it doesn't really matter, but
Oh, okay.
you know, maybe it's more readable. I don't know. Let's check to make sure we didn't make a mistake. I want to remind everybody that we could put this function definition below main. But if we do that, it says my maximum is undeclared. So we need to do what's called a forward declaration. Is that?
Prototype, you mean?
Yeah, this is a function prototype. This is also called a forward declaration. You tell the compiler, hey, my maximum returns an int, and it takes these arguments. I'll tell you the implementation later. Or maybe the implementation is in another compilation unit, in another file. And so now the compiler will accept this, and then the function is defined down here. So that will work. Let's see. So now it compiles and of course runs. So that's the alternative organization. You could even put this in another file. We don't even need that. Look at that. So I'm putting this function in its own file. Oh, not that one, ex. So we just declare this here. And removes the definition there. I'll get an error here. Does anyone know what that error is?
Which error?
Huh?
Not including your function.
Yeah. It's a linker error. It's saying, hey, you told me there's a function called my maximum. I believed you. So I compiled it. But when I go to resolve that function call, I can't find an implementation for my maximum anywhere. And so, and that's called a linkage error. So we have to compile both compilation units together. You see that? Oops. Okay, that's just a side thing, you know. It won't be tested on that. That's just for your knowledge. All right, how about this other one, appending integers? Now we'll talk about vectors. And a vector is sort of an improved version of arrays. So using vectors should be easier than using arrays. You get more functionality built into vectors than you do with arrays. So here's the function signature, we call it. That's what the function looks like without its definition. It's a void function, so my stub code, I don't need to return anything because it's void. It still is a stub. By the way, this vector is a class, but it's a class that's provided to you by the compiler. When you install the compiler, you get these predefined classes.
Don't you have to use pound include vectors?
Exactly. That's right. That's what I was getting up to.
Sorry about that.
No, that's good. I think that's the way you should say everything I'm going to say. You know, just a moment before, and then I know you're paying attention. That's great.
I'm a pretty awesome student.
Yeah, then you can come up here and I'll sit down and relax, and you finish the lecture. Okay, so let's go ahead. Let's see if this compiles. All right. Let's read the instructions. Provide an implementation of the function whose declaration is shown above. The first argument of the function is a vector of int, and the second argument is the number of consecutive integers to append to the vector starting from 0 and ending at n-1. The function appends onto the vector v the values 0, 1, 2, ... n-1. So whatever vector comes in, we simply append a sequence onto the end of it. Use the pushback function of vector to append these values to v. That's the hint. Write test code that thoroughly tests the function. The test code should use assertions. All right. So we have a vector of int. I'll call it v. We don't have a nice initialization syntax for vector, unfortunately. At least I don't think we do, unless it's been added recently. So we need to build the vector. We start with an empty vector v here, and then we call then we insert numbers into it. And the standard way to do that is to call this pushback function. It's v.pushback. It's just like our school bus, our egg carton class. I get an instance of egg carton, go egg carton dot add students. Okay? So it's a class. So vector is a class. We already looked at how to define our own classes, but here vector is a class that has been defined for us already. We just need to use it. So v.pushback 3. And then we could have an assertion here. Let's just practice what we understand. So the way to access items in a vector is the same as accessing items in an array. We use the same syntax, that is. So v of 0 should be 3.
And 3 is just some random number.
3 is the 3 here that we picked, yeah.
Mm-hmm.
Anything.
But I mean, from 3 from the.
Exactly. Just whatever. These have to agree.
Okay.
We just pick this test code. So it's random in the sense that it's random test code. This is how to access the value at a position. You use the square brackets following the name of the vector variable. And inside the square brackets, you place the position in that sequence, what you want to look at. Give me the value at position 0. Once you give me that value, I'm asserting that that value is 4. There's another thing that we could assert. We can assert that the size of the vector is 1. It only has a position, it only has a value of position 0. So its size should be 1, as one element. I think I'm going to put that here. Now, when we call the function, we call append, we pass in v, and say we'll pass in a 2. So v should now look like the following. It should be our first number 4, 0, 1. Because remember, this appends, I'll put a comment here.
Oh, because it's n minus 1.
Yeah. Append 0, 1, all the way up to n minus 1 onto v. So 2, we would append 0 and 1. Well, that's a small example. So when this is done, whoops, the size should be 3. Well, this will fail because we only have a stub right now. We don't actually change n. The size of v is not 3. That's because we didn't modify v. Now we have to do it here. We'll use a loop. We need to append from 0 to n minus 1, so strictly less than n. So I know that I have to generate the sequence of values, 0, 1, 2, all the way up to n minus 1. I have to generate that sequence of values. And for each value that I get, I push it back onto the vector.
Would it have been different if we had said I is equal to 0 to I is equal to less than or equal to n minus 1?
No, that's the same thing.
Oh.
That's the same, gives you the same result. The only difference is this would not be the standard practice. A programmer would not do it like that. A programmer would tend to do it like that. So the other way may make more sense to you now. But if you get into this as a discipline, you're going to have to read a lot of other people's code. So it's easier for you if you follow those conventions. But it's also useful to buck conventions as well. So, you know, I don't want to overly encourage conventionalism. Some languages don't start at 0. The Lua is a scripting language that doesn't start counting at 0. It starts at 1. Lua is a scripting language that's used to be used a lot in video games. It's not used as much anymore, but it was pretty big. It was the biggest scripting language in the video game industry for a number of years. And then in that scripting language, they start counting at 1. So their arrays or sequences start with position 1. But that's the only example that I can think of. All other languages start at 0 that I know of. So let's push back what? Huh? And we're going to push back
V, right?
V? Well, V is the vector. We can only push back integers. Huh? N? Now, N is here. N is 2, so the vector would be 4, 2, 2. If we push back N, then V wouldn't become 4, 0, 1. V would become 4, 2, 2.
Back I.
Yeah, if we push back I, we're going to get 0, 1. That's what we need. We need to push back I. You know, the problem is it's contrived. It's kind of a meaningless problem. So that makes it a little harder to deal with. But we're just appending a sequence from 0 to n minus 1. That's it. And I takes on the values in that sequence. So we're going to push back I. All right. I think that's going to do it. And there we go. It passed our test. The size becomes 3. Oh, but we need to test a little more. Let's do this. Let's suppose we pushed back n. Okay? Will our test code catch this? No. All the test code does is checks the size, that it's 3. And that'll be the case because we're going to have 4, 2, 2. Ah, what happened? Oh yeah, right, it passes, right. Yeah, I was looking for failure.
Logic's off.
No, that's right. So it's passing. It shouldn't pass. That's the problem. So the value at position 0 is 4. But the value of position 1 and 2 should be 0 and 1. Now, because we pushed back the wrong value, now our test code will catch the bug. I guess what I'm trying to illustrate now is why it has to be I, and also why you have to pay attention to your test code. When you write test code, you have to write it to break your program. See that first value. It even shows it to you. V1 equals 0. That line, this is line 24. It tells us the line number where the assertion has failed. It even prints that assertion. V1 equals 0. Line 24. I'm going to jump, colon 24. I'm going to jump right to it. That's the failure. And now we can go back and look. Oh, yes, we should be pushing back I and not N. We fix the bug, run the test code, we got it. So, you know, writing test code is not trivial. You have to think about it, and it's important to test to what are called boundary cases. Here, I can't really think of a good boundary case other than passing it an empty vector v, perhaps, or n set to 0, something like that.
Are you touching Christina right
There's another thing I want to talk about here.
now? Yes. Oh my God.
That ampersand right there. You should all understand this completely. This is important. What does that ampersand do? That means v is a reference to the vector. It's not a copy of the value passed into the... Normally, if we did this, we took the ampersand out, the compiler will generate machine instructions that makes a copy of the first argument that's passed in. So, for instance, where is it? Oh, append here. So here, when we call append, the compiler generates code that makes a copy of v. And then when we do v.pushback_i, we're operating on a copy of v. We're operating on a copy of what got passed in. We're not operating on the thing that was passed in. A copy of the first argument is made because it's called pass by value. You give me a value and I make a copy of the value. Just like this n, we can modify n inside the function, but it won't modify, well, we can't modify. N takes on the value 2. Here, v takes on the value of the v that we passed in. It's a copy operation. So now I removed the ampersand, and based on what I said, which I know is abstract and hard to understand, that's the result when I compile. Will it compile, first of all? It will, I'll tell you that. It will compile. Let's verify that. It compiles. Will it say all tests passed? Or will an assertion fail? An assertion will fail. Which assertion? This assertion is okay. Well, see here, these assertions before we even call append. Here we call append. Will the first assertion fail or not? Now, what's the size of v before we call the function? It's 1. What's the size of v after we call the function? Should be 3. But here, we didn't modify the vector. We modified a copy of the vector and then discarded the copy inside the function. So this should fail. We didn't modify v. Its size is the same. Its size is still 1. v.size equals 3. You see that? This is called a reference. Now we're telling the compiler, hey, compiler, don't make a copy of v. When the function runs, I don't want a copy made of v. I want to modify that v. I want to change the v. My job is to append values to v. I need to modify the v in the calling code, not my copy of it. And so please, compiler, give me access to the vector in the calling code. Don't give me a copy. That's what this reference means. V is a reference to a vector of int. That's how you read that. V is a reference to a vector of int. If I leave this out, V is a vector of int. Of course, when the function runs, a copy is made. actually, it's still a copy. It's V is now a, this V refers to the same vector that, that this V refers to. But the reference itself is different. So I could actually change that reference. Let me fix, just go back and watch that run. It's okay. Yeah, I've never actually done this, but I think that this will work. I could do something like this. No, I'm not gonna bother. Can't do that. Well, maybe I will. Let me do that. Let's. If we have another vector, say of int, and I think this is going to work as an example. Call it W, and then we can set V to W, and the compiler will take that. But why is the assertion? So V is set to W. Oh, I got to think about that. That didn't work the way I wanted it to. Okay. That's, I got to tell you, what we covered today in these first two exercises pretty much covers all the new material for vectors and arrays. And all of these other problems are just variations of what we talked about. No, one difference there, we do have a two-dimensional array here. So perhaps on Monday, we'll talk about this particular exercise, or in lab. I can discuss this with you in lab as well. Everything else is, here's another two-dimensional array. All right, that's it.